Hi, everyone. Okay, we are all done with our exploration of vector operations, and now there's just one more little thing I want to do before we get to the projective plane. So this is just a quick video about the equation of a line, just to remind you where it comes from, and then we'll move on to the projective plane and homogeneous coordinates.
Okay, one last small detour before we get to the projective plane and homogeneous coordinates, which is the point here, is the equation of a plane. So maybe this is just review, but just quickly. So the standard equation for a plane is ax plus by plus cz equals d. And what I want to show is what's important for when we're doing the plane, the projective plane, is that when you have a plane, you have a vector that's perpendicular to it. And I just want to show you the relationship between this and the perpendicular, the vector normal to the plane. So it's a really interesting thing that the normal, it's kind of odd at first, but the normal vector determines the plane because there's only one that is perpendicular to every single angle, to every single vector on this plane. So any vector you have on this plane, there's one vector that's going to be normal to every one of them. So that's how, like, if you think about it that way, then the normal locks in the plane. It determines the plane except for how much it shifts up and down along the normal vector. So I just want to show you that if you have that this is the equation of the plane, then AI plus BJ plus CK is the vector normal to the plane. So you can literally, if you have the equation for a plane, you can literally read off the vector normal to the plane. I just want to show you why that's true. So we'll start, let's just say we have a normal vector to the plane. And then let's say we have some point P1 on the plane, which we'll say is P1, P2, P3. And then in addition to that, so this is a specific point on the plane, but in addition to that, we have any arbitrary point anywhere on the plane. Call that P, which is X, Y, Z. So for this point isn't fixed, it's anywhere on the plane, but from point P1 to this point, no matter where that point is going to be a vector that's going to be on the plane, right? Because these 2 points are both on the plane. So this vector is going to be on the plane no matter what that vector is, no matter where this point is. There's a vector here, whatever. And all of them are perpendicular to n. So this vector is, I guess I should have drawn it the other way, I think. P1 is P minus P1. And so P minus P1 equals, so it's just X minus P1, Y minus P2, Z minus P3. So now again, this is the same thing that we did before. This is the same thing that we did before, where no matter what this vector is in the plane, it's going to be, if it's perpendicular to n, then the dot product of two perpendicular vectors is 0. So we can just take the dot product of P minus P1 times n equals 0. And let's see what we get. So we just have n is ABC. So we have A times, here. we have A times x minus P1 plus B times y minus P2 plus C times z minus P3 equals 0. Multiply that out, we get AX minus AP1 plus BY minus BP2 plus CZ minus CP3 equals 0. Leave the x, y, and z on the left, move all of these to the right, and we have AX plus BY plus CZ equals AP1 plus BP2 plus CP3. Now, these are all constants, right? Because A, B, and C we already know. We know what the normal is. X, Y, and Z are the only variables because they can be any point on the plane. But this point is also constant. So this value is constant. Just say that that's D. And what do we have here? We have AX plus BY plus CZ equals D. That's the equation. That's the equation of this plane. So we started with the normal vector and a point, and then what we end up with by taking the dot product of any vector in the plane with the normal, you end up with AX plus BY plus CZ. So any point XYZ that satisfies this equation is going to be on this plane. So this is the equation for that plane, and the normal vector is right there. And if you think about it, except for D, and all D does is move the plane up and down this normal vector, like this, in some way. The normal vector doesn't move. When you change D, all you're doing is changing the sort of the height of the plane, but you're not changing the orientation of it. So if you just let this be 0, then this is the dot product, right? It's the normal vector plus whatever other vector is on the plane. So that's it. Okay, that was just a quick reminder of the equation of a plane, how you get the normal vector to the plane from the equation, and why it's so straightforward and easy. So keep that in mind. We're done with this, with the vector stuff, and now it's time to move on to the projective plane.
Okay, that's it for the equation of a plane. Now we're all done with the brief review of vector operations, and we're ready to move on to the point of this little series, which is the projective plane and homogeneous coordinates. So please come back. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.